Hi, and welcome everyone to this week's 1W-Minds seminar. It's my great pleasure to introduce our speaker, Dr. Rob Weber, who is an assistant professor of mathematics at the University of California at San Diego. So his research specializes in randomized numerical methods and their applications in data science and scientific computing. Specifically, he focuses on large-scale iterative methods that leverage randomness to overcome the limitations of traditional algorithms, as well as interdisciplinary applications such as chemistry, astronomy, and geophysics. Today, we get to hear him talk about randomly sparsified Richardson iteration. So I'll turn it over to you now, Rob.
Cool. Thank you so much for inviting me to talk today. I'm excited to present some recent work. My name is Rob. I'm a newly minted assistant professor at the University of California, San Diego. So, this talk is about extreme scale matrices. And I'll give you some examples of extreme scale matrices that are as large as 10 to the 108 by 10 to the 108. And I'll convince you, hopefully, that these matrices do arise in applications. And maybe we'll begin to talk about what are some systematic ways to do linear algebra with such extreme scale matrices. To give background, I would say that in scientific computing, we often do need to solve extreme scale linear systems and eigenvalue problems. And if you're really given something this large, like 10 to the 108 by 10 to the 108, dense factorization methods are going to be a non-starter. Iterative solvers are cheaper, but too expensive. And so you might think of a radical approach, which is Monte Carlo. Monte Carlo, in some sense, definitely pushes the limits of the biggest examples that scientists can handle. So, for example, I'll talk about quantum chemistry matrices that are as large as 10 to the 108 by 10 to the 108. And then you can even think of Monte Carlo sampling in continuous space. So you can think that the dimensions are formally infinite, and yet you're coming up with some sort of approximate solution to these infinitely large systems. I am in this field of randomized numerical linear algebra. That's where I do most of my research nowadays. And I'm motivated because I think Monte Carlo methods can be pushed even further and they can be really fine-tuned. But first, their limitations need to be addressed. So, one limitation that you might see is you might actually see some unstable performance in practice. And we definitely want to come up with robust algorithms that perform stably. There's a lot of theoretical questions, which I'm especially interested. The boundaries of applicability are not especially well known, and I'll present today a little bit of progress. As the next frontier in randomized numerical linear algebra, as a new topic that hasn't been sufficiently explored in the past, but it is really, really ripe for exploration, I argue we need to understand and improve these fundamentally Monte Carlo methods. So, in quantum many-body problems in particular, we get these huge eigenvalues. We get matrices that are as large as 10 to the 108 by 10 to the 108. And obviously, even storing a single vector of this size would be unmanageable. You might wonder, where do these matrices even come from? How do you even get matrices where the number of dimensions is bigger than the number of atoms in the known universe? And there's really one way I know that such big matrices arise, and that's combinatorics. So in the case of quantum physics, this would be a Hamiltonian matrix, and it would be calculated in a basis that grows combinatorially fast with the number of electrons or the number of spins. So if it's an electronic structure problem, the number of ways that you can assign n electrons, like 100 electrons, to m orbitals, where m is like 200, is already bigger than 10 to the 108. And you, in general, would have m choose n basis elements. Assigning n spins to plus or minus states leads to 2 to the n basis elements. So again, there's this exponential growth in the number of basis elements. Here's an example of the matrices for increasingly large systems in quantum physics, where we might want to calculate the dominant eigenvector-eigenvalue pair. This is called the transverse field Ising model, and you can instantiate it with any number of quantum spins. Here's what the matrix looks like with 2 quantum spins. Here's what it looks like with 3 quantum spins. And if you really stretch your imagination, you can think of a matrix with 4, 5, 6 quantum spins. There's this beautiful tensorial structure that's emerging. And you might notice that there's some nice things about this matrix. I mean, the size is not nice. It has dimensions 2 to the n by 2 to the n, where n is the number of spins. But the sparsity is nice. There are just n plus 1 non-zero entries per column. So in general, we're interested in problems where we can read a single column or generate it in sparse format, but we can't look at a significant fraction of the matrix simultaneously. So that's the type of scaling that I'm talking about with extreme scale. Now, for non-extreme matrices, there's a lot of ways to get the dominant eigenvalue and associated eigenvector. A lot of folks use iterative eigenvalue solvers like the power method or subspace iteration, the Lanczos algorithm for a Hermitian matrix, Jacobi-Davidson method. The power method is the simplest approach for finding lambda max of A. And all you do is you evolve some iterates x sub t through a multiplication with A and a subsequent normalization where you divide by the norm of the current iterate x t plus 1. So this works. I mean, it works if there's a spectral gap. It's going to converge to the eigenvector associated with the largest magnitude eigenvalue. There's a couple ways that you could estimate that eigenvalue, and this is actually important for the remainder of the talk. Way back in the day, I learned this. People used to estimate the largest magnitude eigenvalue by taking some test vector, x naught, and calculating the inner product with axt divided by the inner product with xt. So this is a historical eigenvalue estimator that people used to use. The modern approach, which converges faster, is a Rayleigh quotient, where you take the inner product of axt with xt divided by the inner product of xt and xt. And there's some familiar theory about the convergence of the power method. If you've got a symmetric matrix, real valued in this case, but we could, think about Hermitian matrices with complex values. If it's got largest magnitude eigenvalues, lambda 1, lambda 2, this is weakly decreasing order by the magnitude, and associated eigenvectors, and we define maybe an initial overlap and a spectral gap, then the eigenvector estimates are going to be getting really, really, really close to the dominant eigenvector, exponentially fast in R. R is the spectral gap, and depending on the initial overlap. And you can see as you look at these two eigenvalue estimators that there is also exponential convergence, and it's going to be R to the t for the historical eigenvalue estimator and R to the 2t for the Rayleigh quotient, the modern eigenvalue estimator. So this means that you should definitely use the modern eigenvalue estimator when it's possible to do so. We can estimate the ground state for small systems in this way by applying the power method to a matrix that is a shifted version of the Hamiltonian matrix. So apply the power method to A is identity minus epsilon h for a sufficiently small epsilon parameter. And the problem, while you can do this for small systems, is if you do it for big systems like these transverse field Ising models or the 10 to the 108 by 10 to the 108 matrix, is you get increasingly dense vectors at each iteration. You're basically getting polynomial fill-in. You're very quickly losing the sparsity of an initial vector. And so this raises a question that a lot of people in quantum physics thought about for a number of years and that I've been looking at lately, which is how can we adapt the power method to larger or even extreme scale matrices? And there's this wild Monte Carlo idea, which has really been explored since the 1950s, but is maybe a little bit left field or unusual, where you introduce random walkers. They're denoted by xc, and there's n sub t of them. And they're hopping around on all these different states, indexed by 1, 2, all the way to d, the dimensionality of the eigenvalue problem. Attached to each walker is a positive or a negative sign. So that'll be s sub t1 all the way to s sub t and t. And these walkers, in this amazing approach in quantum physics, interact in what's called a game of birth, death, and annihilation. This approach is called full configuration interaction quantum Monte Carlo. It's kind of a mouthful, but it's a really cool algorithm. For each walker, CTI, that is currently occupying a state J, what you want to do is, with some probability, PJK, spawn walkers at a new location, K, that's not equal to J. So this is a birth process. And then the number of spawned walkers is going to be random. It's going to be n sub jk, and it'll be here a randomized rounding of AJK divided by PJK. So a randomized rounding in this case is like you take this number, which in general might be between two integers, and then you either round it down or round it up with the appropriate probabilities so that this is the expectation value. Assign the walkers the same sign as the parent if AJK is positive, and assign them the opposite sign if AJK is negative. So that's birth. Death, for each walker, you are going to replace it with some number of walkers, typically like 0 or 1, where the number is, again, a randomized rounding now of the AJJ entry of the matrix. And you assign the walkers the sign STI if AJJ is positive, negative STI if AJJ is negative. Annihilation, you've got these positive signs, these negative signs, and they annihilate. Cancel two walkers on the same site that have opposite signs. This is the probabilistic setup. It's a little bit confusing, even though it's very popular in quantum physics. And you can think about it as approximating a matrix vector multiplication in the sense that it's producing some xt plus 1 whose expectation value is axt. If we define xt to be the sum of all the signs times delta functions at the Walker locations at time t, and we define xt plus 1 to be the same sum of signs times delta functions at the Walker's locations at times t plus 1. So this is a vector, this is a vector. The expectation value of this is this, conditional expectation. And the birth step is really performing the multiplication with all the off-diagonal entries of A. The def step is performing the multiplication with all the diagonal entries. The annihilation step is performing the addition, where A is the sum of its diagonal component and its off-diagonal component. And the only kind of tricky business with this FCI QMC, this full configuration interaction quantum Monte Carlo, is maybe you're going to get systematically too many walkers over time. Maybe it'll be increasing at every step. Conversely, I mean, it might have a population that's dwindling and get really close to zero. And so the way that people end up implementing this is they end up having a dynamic shift, which is adjusted to kill off more walkers if you're getting too many, or to create more walkers if you are getting too few. So here's a picture. I don't know how good or informative it is, but this is taken from the quantum physics literature. And you can see that there's two different signs indicated in orange and blue. And then there's the effect of a matrix multiplication. You can see that there's a birth going on, and birth can either lead to walkers with the same sign, or it can lead to walkers with the opposite sign. And this would be due to positive and negative entries in the matrix. And then you can also imagine that there's going to be a little bit of cancellation, right? One of these blue walkers will cancel with this orange walker. So this is kind of a picture illustration, but this is implicitly solving an extreme scale eigenvalue problem. It's an amazing algorithm, and I started looking at it at the very beginning of my PhD, which was back like too many years ago. And, one of the things you might think about is, does it even converge? We're targeting the dominant eigenvector of this gigantic matrix, but we've got a stochastic algorithm that's probably going to have a lot of variance. Can we prove that it converges? From the description, you can think about this as a Markovian system. And generally, for Markovian systems, you would anticipate that they converge to a stationary measure. So maybe this is an approach like we could try to prove that they converges to a stationary measure. And you would also anticipate that given that the system is in the stationary measure mu, that this random vector of signs and Walker locations lies really close to the ground state. The ground state is this dominant eigenvector that we're targeting. Because it's a Markov process, you would then try to estimate the ground state energy using trajectory averages. And you can do this. This is exactly the historical eigenvalue estimator, where you're taking the x0 and you're looking at the inner product with some time average of the AXRs produced by this algorithm, and you're dividing by the inner product of x0 with some time average of the XRs. This will give you an eigenvalue estimate. It's a ratio of averages of a Markov chain, and it would have convergence rate t to the negative a half. Not the fastest convergence, but it's a start, right? So I was interested in that system, and the problem was I could never really prove anything about it. It turns out that there was a lot of really technical details that were just so challenging about the convergence to stationarity. But we started to work on simplifications and stabilizations to make the algorithm better, and this proved to be a more fruitful line of development. I mean, why do you have to do the walkers? Why do you have to do the signs? Why don't you approximate a matrix vector multiplication a little bit more directly? So the idea, and this is work with my PhD advisor, Jonathan Weir, was to introduce what we called a random compression operator that can be applied to a vector in order to sparsify it. So this is random compression or random sparsification. Lately, we've been calling it random sparsification. It outputs a d-dimensional vector that has at most m non-zero entries. So even if it takes as input something that's very dense, it outputs something that is m sparse. It is unbiased, so the expectation of phi x is just x. And then if you can introduce such an object, why not take the guiding principles behind full configuration interaction quantum Monte Carlo and just use this sparsification operator instead? So we are using a simple iteration where we sparsify, multiply, normalize. Sparsify, multiply, normalize. It's very, very close to the traditional power iteration, except that there's iterative random compression or random sparsification. Again, we approximate the dominant eigenvalue of A using this historical eigenvalue estimator, and we anticipate a t to the negative a half convergence rate. So the first thing that this broader perspective opens up is maybe the methods that were being used in quantum physics could be optimized. Maybe we can choose a compression operator that is somehow optimal. And so I formulated this problem in what I thought was the most natural way and came up with a solution. For any d vector x, the compression operator phi that minimizes the expected norm square of the difference between phi x and x is characterized by three pretty simple steps. It's got to be a random compression operator that preserves the largest magnitude entries exactly. So that means if there's some high magnitude entries in the input, they're just going to remain exactly the same. And so particularly here, we've introduced some permutation of the indices that gives us the first highest magnitude k indices as sigma 1, sigma 2, all the way to sigma k. And those are maintained exactly. So we're just going to maintain the largest magnitude entries exactly. The smallest magnitude entries are more interesting. They're randomly sparsified, and the optimal way to do this is as follows. You take the input entry, xi, and with some probability p sub I, you got to make it bigger. You got to do this because of the unbiasedness constraint. But with the remaining probability 1 minus pi, you set it equal to 0. And we calculated the best way to do this. The optimal PIs take this particular form where they are proportional to the magnitude of the entries. Last, there's a question, how many do you exactly preserve? How many do you randomly sparsify? The choice that minimizes the mean square error is the number k should be as small as possible while ensuring that all the p's, by this definition, are less than or equal to 1. So that's kind of implicit, but you implement it on particular vectors and it makes sense. So here is a vector that's just a small schematic so you can understand what the optimal compression, optimal sparsification is doing. A priori, the vector has 7 dimensions and it's got 5 non-zero entries. And let's say we want to do a really big sparsification. We want to get it down to just 2 non-zero entries. What you ought to do, what the optimal method does, is it preserves the highest magnitude entries. And then it randomly samples one of these 4 small magnitude non-zero entries with probabilities 2/5, 1/5, 1/5, 1/5. And then it outputs either negative 0.25 in the selected index or positive 0.25 in the selected index, depending on what the sign was. I know this is a lot to take in, but is this heuristically clear? Do people understand what this is doing kind of heuristically? Or are there any questions? We'll take silence as evidence that this is exceptionally clear and there are no questions. Cool. So, continuing on, we implemented this method and got a pretty intriguing pattern of results. So, there's two different things that you're doing. Oh my gosh, I see chat. Makes sense so far. Oh, fabulous. So that's what people did. Okay, so they put it in the chat. I appreciate that. Thank you. Um, there's two parameters, right? There's how long do you run the algorithm? Okay. And so here you're seeing like 30,000 iterations. And then there's what's the sparsity level that you're going to be using. Okay. And as you run the algorithm for longer, you get this Monte Carlo scaling. So everything, all the errors are going down at a rate t to the negative a half. But what's happening with the sparsity level? I mean, the sparsity level, you might think, okay, maybe that should be Monte Carlo scaling too. Maybe that should be m to the negative a half scaling too. But this isn't m to the negative a half scaling. What you actually see when you implement this is that you're getting garbage estimates with 5,000 elements, with 5,000 sparse vectors. And then you're suddenly getting way better estimates with 10,000 sparse vectors. And once you get to 50,000 sparsity level, you're just not seeing any variation at all. Like it's really, really low variance. So that's intriguing. I mean, that's the biggest question related to these methods. What is the role of the sparsity parameter? Alternatively, what is the role of the number of walkers in a traditional FCI QMC method? How do we expect performance to scale with the size of these parameters that are ultimately controlling the computational cost and controlling the sparsity level of the approximation? We implemented our method on a bunch of systems in quantum physics. These are some simple atoms and molecules. And we saw that indeed the statistical efficiency, which is, sort of the amount of precision you're able to get, is way, way better if we're using this FRI method as compared to the FCI QMC method. We're getting much, much more accurate estimates. And the only reason why this didn't change the world is because we were doing more computational work for every iteration than FCI QMC. It was just a little bit more costly to actually calculate these optimal sparsifications as opposed to using the walkers that were randomly hopping between different places in state space. So maybe our method works, but maybe it's not the most practical method. Unfortunately, we worked on this for a while and we found it hard. So John Weir and Likheng Lim introduced FRI in 2017 in a SciAm review paper. John and I worked with chemists Tim Birkelbach and Sam Green to adapt FRI to dominant eigenvector problems and dominant K eigenvector problems. So we were able to extract multiple dominant eigenvectors, those associated with the largest magnitude K eigenvalues. And try as I might during the PhD and even subsequently, I couldn't come to much mathematical understanding of when FRI methods for eigenvectors succeed versus fail, what would be the important matrix properties? I mean, obviously a spectral gap helps, but I wanted a more fine-grained understanding, and I found the analysis to be technically difficult. 8 years later, I'm finally starting to prove error bounds for sparse approximation of dominant eigenvectors. So I've made some progress. There's a forthcoming paper. I'm pretty stoked. It's not ready to present yet. But what I will present is that John Weir and I recently extended FRI, this stochastic method based on iterative random sparsification, to linear system solves for the first time. And we established a pretty clean convergence proof that I think is interesting in its implications for high dimensional linear algebra. So that's the rest of the talk. And we'll jump into it. We were interested in a linear system of equations that is formulated as this fixed point problem. X is gx plus b. And we were looking at the special type of linear systems where G is a contraction. It's a matrix contraction, which means its eigenvalues are smaller in magnitude than 1. Many linear systems can be rewritten in this form. For example, all strictly positive definite systems can actually be written in this form if you just multiply by a small enough epsilon parameter and then set G is identity minus A. There's a really classic, simple method for solving these fixed point linear systems of equations, which is called Richardson iteration. And all you do is you start with x0 is 0, and then you do a multiplication with g and an addition of b. So xt plus 1 is gxt plus b. Just multiplication, addition, multiplication, addition. It's got a really good convergence profile. In an exact calculation, the tth iterate is the solution vector x star minus g to the tth power times x star. So, very directly, you can see that the error is decaying at a rate that's determined by the spectral radius of g. Richardson iteration is a cool algorithm. And the problem, again, is that it requires a full pass through G. If your vector is dense, and in any case, there's going to be very, very rapid fill-in. You're going to lose your sparsity. It's expensive. It's really expensive to implement this if you have a dimension that's a lot bigger than 10 to the 5. So our idea was to adapt random sparsification, randomly sparsify each iterate so that each matrix vector multiplication runs a lot faster. So here is our algorithm. It is a simple modification of Richardson iteration. You again start with 0, but before it was multiply by the matrix, add the vector. Now it's sparsify, multiply, add. Sparsify, multiply, add. And again, we're interested in this random compression operator, same one we used before, so that phi of x for any input x has at most m non-zero entries, and its expected value is the input x, so it's unbiased. And again, we can kind of think about like the historical eigenvalue estimator. We can think about what happens in Markov processes, and we can realize that the compression is going to introduce errors, but those can be reduced by time averaging. So we can use this estimate, I'm calling it xt bar, where you take a trajectory average starting from some burn-in time b and going to a final time t. This approach is surprisingly amenable to analysis. So here's the result that we managed to prove. And I guess we first pushed this to the archive in 2023, and it's probably going to be published in 2025. Consider the algorithm on the previous page. Consider randomly sparsified Richardson iteration applied to any problem of the form x is gx plus b. And I'm not giving you the most general thing because it's a little bit more complicated. I'm giving you a special case where G and B are non-negative valued. The one norm of G is less than one, so it's a strict one norm contraction. And the sparsity level is greater than or equal to the reciprocal of one minus the one norm of G. So if these conditions are satisfied, then you get a bound on the mean square residual, the expected mean square residual, which is the sum of a square bias term and a variance term. The square bias term decays exponentially fast, depending on the burn-in time. So it is going to be something that you can control with a constant number of iterations, assuming that you've got a decent spectral radius for G. So this is totally fine. This is a dimension independent bound. It has nothing to do with the dimensions. The variance is a little bit more complicated. The variance has 8t over t minus tb square. So it's kind of like a 8 over t type of term. And then there's this intriguing quantity. And this was the whole point of the analysis, and this is what's so amazing and inspiring. We are introducing the decreasing rearrangement of the solution vector. The solution vector in this case is going to be non-negative valued. And so we're just going to introduce a weakly decreasing rearrangement. And we've got a variance term that tells us we don't even have to take into account all the entries of the solution. We can actually pick some I parameter, which is a little bit less than our sparsity level. Like our sparsity level is 2000. We can pick I to be 1000. And then we just ignore the 1000 largest magnitude entries of the solution vector. Our variance is only determined by the small magnitude entries. So imagine a solution vector that's exponentially decaying. We don't even care that there's some large entries. We only care about the small ones. That's the only thing that affects our variance. I think this is an unusual expression. I'm going to try to make it a little bit more practical and real to you on the next few slides. So the random compression contributes a variance term that decays at a rate that's at least 1 over mt, but it can be a lot faster depending on the decay of the solution vector entries. And so this is the real part of the story that I want to share. I'm going to share it with a particular example first, because I like examples. Extreme scale linear systems occur in many settings. So there's examples in quantum many-body problems. Another example, which is kind of exciting, is the internet. And here's a picture, an artist's rendition based on some facts of the internet in 2010. There's a page rank problem that's kind of famous where you're ranking pages in the internet. At time t equals 0, an internet surfer chooses a random site with some personalized probability vector pi. Like, for example, I probably watch too much YouTube. So my personal probability vector pi might put 50% probability on youtube.com. And then at each subsequent time, the surfer clicks on a random hyperlink with probability C. So like I have an 80% persistence rate, C is 0.8, and otherwise chooses a random site with probability vector pi. So maybe I get bored of the current chain of Wikipedia links that I've been following, and I just go back to YouTube. The question asks, as t goes to infinity, what is the fraction of time spent visiting each website? And here's a picture I got from Wikimedia Commons, where, the only input would be the system of hyperlinks. And maybe for this system, you would just consider pi to be uniformly distributed. And you can sort of see which websites are important according to the PageRank problem. It's a reasonably good way to rank websites, although you might argue that C should not be so important. In terms of linear algebra, let P be a column stochastic matrix which encodes the value 1 over k if site j has k greater than 0 outgoing links and I is one of the links. So it's column stochastic. It's kind of giving these transition probabilities. And then it would just be Pij is pi I if site j is kind of without any outgoing links. The PageRank vector x solves this problem, which is exactly the right type of linear system for us to attack using randomly sparsified Richardson iteration. Indeed, when Sergey Brin and the Google guys came up with PageRank, they were solving it according to their publication using Richardson iteration. This is how they were solving it. They found that it converged reasonably fast, like 50 iterations sufficed for the entire internet as they had compiled it back in, I believe, the 90s. And the problem is the internet's a lot bigger nowadays, and quantum physics problems are even bigger than the internet. So maybe Richardson iteration is not going to work anymore. People have advocated Monte Carlo sampling, where you literally simulate the surfers, count the fraction of time spent visiting each website. And the problem there is that it's just a little inaccurate. So, there's a lovely set of SciEm papers that talk about this approach, and there's clean error bounds, but you can't really get beyond those Monte Carlo convergence rates. You can't get beyond an error scaling that's 1 over the square root of the number of walkers. Randomly sparsified Richardson iteration for this problem is often about right. And we remember it's just the same as Richardson iteration, except that you randomly sparsify before the matrix multiplication and before the addition. I implemented it. I actually ran the tests. I programmed my method. And I found a very clean pattern of results, which was exactly what I proved in the theory. So what we're seeing here is we're seeing on the left something that I'm calling PageRank tail decay, which means for 3 different PageRank problems, including Amazon Electronics, Notre Dame websites, and flights, there's a solution vector that if you put it in, weekly decreasing order from biggest, smallest magnitude elements, you can just add up the tail. You can just say, how big are the smallest guys all put together? And that's what I'm plotting right here. And you can see for different problems, the PageRank solution vector is decaying more or less quickly. It's really decaying quite quickly for Notre Dame websites. This is like Notre Dame, the university, has a web system, and I guess it's highly centralized in a few important web pages. The right panel shows the error, in this case, the root mean square error, that's actually attained by the algorithm with sparsity level m. And what's sort of amazing, I mean, in every case, we're pretty much seeing it's better than you would get from a Monte Carlo algorithm. But we're seeing pretty much the right panel is the left panel multiplied by a factor of m to the negative a half. We're basically seeing however fast your solution vector is decaying, we're going to get that error level, and then we're going to give you an additional m to the negative half, the Monte Carlo rate. So this suggests that as long as you have an actually super fast decaying solution, you can recover it with super high accuracy. That's what's exciting about this pattern of results. So, Kevin, how am I doing on time? I can go through a proof or not.
So you've got about 10 minutes, I'd say.
Let's do the proof. Let's do the proof. I'm kind of excited about the proof, so I'm going to do the proof for you. Okay. So this is kind of the big result of our analysis. And so one question that you might have, if you're interested in this sort of thing, is how do we prove this result? How do you actually prove this kind of unusual bound? Someone said, bust out the proof. So, you could probably start with a standard bias variance decomposition. So usually a mean square error is the sum of a square bias term and a variance term. Here we happen to be dealing with vectors, but a version of the statement is true as well. So this holds with equality. I mean, this holds for anything. And it turns out for this randomly sparsified Richardson iteration, the square bias term is really easy because on average, this is producing exactly the same vectors as deterministic Jacobi iteration. It's actually a linear algorithm, with some unbiased perturbations. So you can calculate this exactly. I mean, here's an exact expression for the bias. It's this time average because we're doing the time averaging. And it's upper bounded by g to the TB power times b. Because remember, the burn-in time, the amount of time at the beginning that we're not using to estimate the solution, we're just getting rid of those early iterates, they never get counted. And so it's only these later iterates that are already close in expectation to the solution that we're considering. The square bias is so small. It's so small. The variance is the hard part. So let's do the variance. It's subtler, but you can use some martingale tricks, which are, I would say, reasonably standard, in order to see that the variance really only depends on the sparsification error at every time step. At every time step, you are sparsifying a vector. And so it's natural that the variance of the algorithm depends on what is the mean square error as you sparsify all the vectors in the algorithm. Now, we designed the optimal compression so that it leads to, in some sense, the best possible mean square error. So maybe we have some hope that this term is going to be small. Analyzing this term is the proof crux. And this is really like a sketch of proof in the sense that I'm not going to go through all of the details. But what I do want to tell you is, remember how we're keeping some of these large magnitude entries exactly? Well, you can use that. I mean, a direct bound shows that for any fixed vector v and any subset of the available indices, you have error that's going to be bounded from above, mean square error that's going to be bounded from above by 2 over m minus the cardinality of s times the sum of all the indices that are not in the set S, the sum of their associated entries, squared. And so that's really cool. That's a really cool feature of this particular way of sparsifying vectors, which wouldn't be present, for example, in FCIQMC, in full configuration interaction quantum Monte Carlo. The fact that we were so careful with the optimization means that we can kind of exclude any indices we want. They're not really going to be contributing very much to the error. So a recursive argument, which I will acknowledge is a little bit tricky, then establishes that you can take all of these mean square error bounds and you can upper bound them by 2 over m minus mg minus the cardinality of some index set S, and then the sum of entries in the solution vector excluding the index set S. So it's this amazing proof technique where you're saying that actually the error is less than or equal to any index set S, and then you have to pay a little bit for it. And last, we choose the indices S for which X star is largest. So that's, about as good as you can do in like a 3-minute sketch of proof in a presentation. But I think that some mathematical people like myself like to have an idea of like what are the techniques involved and perhaps what are the features of the algorithm that you would use to prove rigorous results. I want to conclude at this point. I think I'm actually doing pretty good on time. I think this is almost exactly 50 minutes. It is fun for me. It is really fun to ponder linear algebra problems where the solution is too large to store as a dense vector. It's futuristic. It's not something people really think about in linear algebra very much. It's unusual. One obvious limitation is that the optimal approximation A x hat that is constrained to have sparsity level m has got to have error. Here it's the square error that is equal to the sum of all the smallest magnitude entries squared. And the thing is, there are cases where you have a solution vector that's quickly decaying, where this can be quite small. So then I would argue the hunt is on to find practical algorithms that give error proportional to the tail. So the elevator pitch for my RSRI algorithm is here is an algorithm that provably gives error proportional to the tail. But I don't claim that it's the end of the story. I actually think that it's the beginning of the story. I'm finally making some progress on analyzing iterative random sparsification applied to eigenvectors. And I think that these questions of extreme scale linear algebra and iterative randomly sparsified solutions are extremely ripe for progress. So it's an area I'm excited about, and hopefully I've generated some amount of excitement today. And thank you for your time.